Good morning everyone. In the last class we discussed power method for computing numerically the largest eigenvalue in magnitude of a given matrix A. So, let us illustrate this method by taking some examples. So, we said that if you are given a square matrix, say an n cross n matrix, we start with an initial vector which we call as V naught, and we find the vectors say y k plus 1 which are a v k, and the next vector v k plus 1 will be vector y k plus 1 by m k plus 1, where m k plus 1 is the largest element in magnitude in y k plus 1 vector. Then lambda 1 will be limit as k tending to infinity of the mth component of vector y k plus 1 by the mth component of the vector v k, and the vector v k plus 1 that we have obtained will give us the required eigenvector. So, let us now illustrate this procedure, which is our method for computing numerically the largest eigenvalue of a given matrix A. So, let us consider the given matrix A to be a 2 cross 2 matrix having entries 3, minus 5 and minus 2, 4. We start with an initial vector V naught, say 1, 1. So, we should find first vector y 1, which is A times V naught. So, it is 3 minus 5 minus 2, 4 into 1, 1, and that is the column vector having components minus 2, 2. Now, I remove the largest element in magnitude and write down the vector as minus 2 times 1 minus 1. So, now I should define V 1. What is V 1? That is y 1 minus the largest value of the element that I have factored out. So, that will give you 1 minus 1. So, with this V 1 I compute y 2 vector, which is A V 1, 3 minus 5 minus 2, 4 into V 1, which is 1 minus 1, and that is 8 minus 6. I remove the element which has largest magnitude and write down the vector as 1 minus 0.75. So, it is 8 times vector V 2. So, we compute y 3, which is A V 2, 3 minus 5 minus 2, 4 into V 2, which is 1 minus 0.75. That turns out to be 6.75 minus 5. So, I remove 6.75 and the vector that I get is 1 minus 0.7407. So, it is 6.75 times vector V 3. We compute y 4, which is A V 3. So, 3 minus 5 minus 2, 4 into V 3, which is 1 minus 0.7407. and that turns out to be 6.7035 minus 4.9628. So, we remove 6.7035 and the vector is 1 minus 0.7403. So, we have y4 to be 6.7035 times vector v4. We continue this process and compute what is y5, and that is a v4. So, 3 minus 5 minus 2 4 into vector v4 is 1 minus 0.7403, and that turns out to be 6.7015 minus 4.9612. So, I remove 6.7015 and we get 1 minus 0.7403. So, we have 6.7015 times vector v5, and we see that every time we perform the computations, the vector is such that the components in the vector are coming to be closer to each other. So, let us perform another iteration and see. So, compute y6. So, vector y6 will be a into vector v5. So, 3 minus 5 minus 2 4 into vector v5, which is 1 minus 0.7403, and that turns out to be 6.7015 minus 4.9612. So, it is 6.7015 into 1 minus 0.7403. And so, this will be 6.7015 into vector v6. So, at this stage we observe that 6.7015 into vector v5 is the same as 6.7015 into vector v6, and therefore, convergence has occurred. And therefore, we can stop our computations and write down what the eigenvalue is and the corresponding eigenvector is. So, we observe that the eigenvalue lambda 1, which is numerically the largest eigenvalue of this matrix, is 6.7015. And what is the eigenvector? The corresponding eigenvector is given by 1 minus 0.7403. So, power method helps us to compute numerically the largest eigenvalue or the most dominant eigenvalue of a given matrix A numerically, and the procedure is illustrated by means of this example. So, let us now take a 3 by 3 matrix A and then work out the details. So, the problem is find the largest eigenvalue in modulus and the corresponding eigenvector of the matrix A, which has elements minus 15, 4, 3, 10, minus 12, 6, 20, minus 4, 2, and we are asked to obtain the dominant eigenvalue of this matrix by power method numerically. So, we start with the initial vector v0 having components 1, 1, 1. I compute the vector y1 first. What is it? It is equal to A into V naught. So, A into vector 1 1 1, where A is this matrix. The entries in the product of these two matrices are given by -8, 4, 18. So, I have to define now my vector V1, which is vector Y1 by the largest element in the vector Y1. So, that will give me -8 by 18, 4 by 18, 1, and that is -4 by 9, 2 by 9, 1. Now that I know the vector V1, I compute Y2, which is A V1. So, A into -4 by 9, 2 by 9, 1, and that turns out to be the vector 95 by 9, -10 by 9, -70 by 9, and I divide by the largest element, namely 95 by 9. So, if I remove that factor, I get a new vector which is V2. So, V2 turns out to be the vector 1 minus 2 by 19 minus 14 by 19. So, we compute Y3, Y4 and so on. So, I leave these computations for you, and when it comes to obtaining the vector Y7, it turns out to be the vector minus 19.8674, 9.7072 and 19.8524, and therefore, I compute vector V7 by dividing vector Y7 by the numerically largest element in that vector. That gives me V7 to be minus 1.0, 0.4886, 0.9992. So, we compute Y8, which is A into V7, and that gives 19.952 minus 9.868 minus 19.956. And so, I compute vector V8, which is Y8 vector by numerically the largest element in Y8, and that turns out to be 0.9998 minus 0.494 and minus 1. And so, we work out Y9, which is A times vector V8, and this turns out to be 19.973, 9.926 and 19.988. Suppose say the problem also says perform 9 steps using power method and write down the numerically largest eigenvalue of matrix A. So, we have performed 9 steps, and at this stage we want to stop our computations, because we are asked to do only 9 steps of computations of power method. And so, we determine the eigenvalue and the eigenvector. So, what is going to be an approximation to the largest eigenvalue? In modulus. So, it is modulus of lambda, and that will be the mth component of vector Y9 by the mth component of vector V8. So, I have to compute the ratio of the first component of y9 and first component of V8. Then take the second component of y9 by the second component of V8 and then get the ratio. The third component of y9 and the third component of V8 and obtain what the value is. So, we get for the first component of y9 19.973 divided by first component of V8 is 0.9998. The second component of y9 is 9.926 and that of V8 is minus 0.494. The third component is 19.988 divided by minus 1. So, I observe that if I compute these ratios and take the absolute value, then round it off to 3 digits, then I end up with mod lambda to be 20. So, if I compute this ratio, it is going to be very close to 19.96 etc. Similarly, this one, and here it is going to be minus 19.988, and I observe that that is the largest. So, in absolute value correct to 3 digits, when I round it off to 3 digits, mod lambda is close to 20 and therefore, that is the largest eigenvalue in magnitude of this matrix A. So, we have to get the corresponding eigenvector. So, the corresponding eigenvector is going to be the vector having components, namely V8, that will give you 0.9998 minus 0.494 and minus 1. So, the numerically largest eigenvalue and the corresponding eigenvector of the given matrix A have been computed using power method. I will give you some problems, you can try to work them out at home, and I will include some more problems in the assignment sheet. So, find numerically the largest eigenvalue of the matrix 1 minus 3 2 4 4 minus 1 6 3 5 by power method. You start with the vector V0 having components 1 1 1. Now, I will give you the final answer, you can try to see. Compute 16 steps of computations and show that at the 16th step you get y16 to be 6.9998 into 0.3000 0.06661, and therefore, eigenvalue, the numerically largest eigenvalue is close to 7. So, using power method we have been able to compute the most dominant eigenvalue. The question now is it possible to obtain the smallest eigenvalue of this matrix A using power method? The answer is yes, and let us see how we can obtain the smallest eigenvalue. So, suppose we assume that a matrix A has largest eigenvalue, say lambda. Then what does that mean? It means Ax is equal to lambda x, and let us assume that A is invertible. Then when I pre-multiply this by A inverse, then I get Ix to be equal to A inverse into x multiplied by lambda. Therefore, 1 by lambda x will be equal to A inverse x. So, when we say that Ax is equal to lambda x, we say that lambda is an eigenvalue of the matrix A and the corresponding eigenvector is x. Now, this statement tells us that 1 by lambda is an eigenvalue of A inverse and the corresponding eigenvector is the same vector x for the eigenvalue lambda of the matrix A. So, this tells you that 1 by lambda is an eigenvalue of matrix A inverse with the same eigenvector x. If I call the dominant eigenvalue of A inverse as mu, so that A inverse x is equal to mu x, then it is clear that 1 by mu is the least eigenvalue of the matrix A. Why? What have we shown? If lambda is a dominant eigenvalue of matrix A, then A inverse x is 1 by lambda into x. So, that if mu is the dominant eigenvalue of A inverse such that A inverse x is equal to mu, then 1 by mu will be the least eigenvalue of the matrix A. So, if I ask you to compute the smallest eigenvalue of a given matrix A, what is it that you should do? Given the matrix A, compute its inverse, say by Gauss-Jordan method, and then compute its dominant eigenvalue using power method. Take the reciprocal, that gives you the least eigenvalue of the given matrix A. And therefore, it is possible for you to compute the smallest eigenvalue in magnitude for the given matrix A. So, let us work out an example illustrating this. So, if I consider matrix A to be given by minus 15, 4, 3, 10, minus 12, 6, 20, minus 4, 2, and I am asked to compute the smallest eigenvalue of this matrix A. So, I immediately compute the inverse of the matrix A, and it turns out to be 0, minus 0.02, 0.06, 0.1, minus 0.09, 0.12, 0.2, 0.02, 0.14. So, I have to now compute the most dominant eigenvalue of this matrix A inverse. So, use power method to compute the most dominant eigenvalue. Start with the vector say V naught, which is 1 1 1, and compute y 1, which is A inverse into V naught, because you are computing the dominant eigenvalue of the matrix A inverse. So, your y 1 is A inverse into V naught. So, continue your computations and show that the dominant eigenvalue of A inverse turns out to be say 0.2, that is 1 by 5. Show that the dominant eigenvalue of A inverse is 1 by 5, and therefore, the least eigenvalue or the smallest eigenvalue in magnitude for the given matrix A is going to be 5. So, given a matrix A, you know how to get the largest eigenvalue by power method and how to get the least eigenvalue by computing the dominant eigenvalue of A inverse and taking its reciprocal, and that will give you the smallest eigenvalue of A. So, you now know using power method how to compute both the largest eigenvalue and the least eigenvalue. There is also another way of computing the smallest eigenvalue of a given matrix A, even without computing what A inverse is. So, let us see how this can be done. So, let lambda be an eigenvalue of A. So, A is a given matrix. Suppose lambda is an eigenvalue of A, that Ax is equal to lambda x. Let us find a matrix B, where B is given by A minus mu times I. Mu is some constant. Then let us compute what is Bx. So, Bx is A minus mu I into x. So, it is Ax minus mu I x. But what is Ax? Ax is lambda x. So, this tells you it is lambda minus mu into x. So, what have you shown? Matrix B, which is A minus mu I, is such that it satisfies this equation, namely Bx is equal to lambda minus mu times x. What are lambdas? Lambdas are eigenvalues of the given matrix A, and therefore, A minus mu I has eigenvalues lambda minus mu, and therefore, the eigenvalues of B are merely the eigenvalues of A diminished by a constant mu. And what about the eigenvector? The eigenvector is the same, namely if lambda is an eigenvalue of A and the corresponding eigenvector is x, then lambda minus mu is an eigenvalue of B having the same eigenvector x. So, that is what we want to write. The eigenvalues of B are merely eigenvalues of A diminished by a constant mu with the same eigenvector. So, therefore, if you evaluate the largest eigenvalue of A and call it as lambda 1, then we can determine the smallest eigenvalue of A by modifying the matrix. We are given a matrix A. We would now like to consider another matrix which is different from A. So, we want to do some modification in the matrix A. What is it? Take it in the form A minus lambda 1 times I. Take the matrix A and subtract the matrix which is lambda 1 times the identity matrix. By what we have discussed, what can you say about the eigenvalues of this matrix? This matrix has eigenvalues given by say lambda p dashed, which is equal to lambda p minus lambda 1 for p is equal to 1, 2, 3 up to n, where what are lambda p's? Lambda p's are eigenvalues of A. Right. Now, I want lambda p to be the smallest. So, for lambda p to be the smallest, lambda p dashed must be the largest in magnitude eigenvalue of which matrix? A minus lambda 1 into I. What are lambda p's? They are the eigenvalues of the given matrix A. So, lambda p minus lambda 1 for p taking values 1, 2, 3 up to n, and if you call that as lambda p dashed, then the lambda p dashed are such that they are the eigenvalues of A minus lambda 1 into I. So, in order that your lambda p, which is an eigenvalue of A, to be the smallest, you must have lambda p dashed to be the largest eigenvalue in magnitude of A minus lambda 1 I. Can you compute this? Yes, we know we can use power method to obtain the largest or the dominant eigenvalue in magnitude of a given matrix. What is the matrix that is given to you now? The given matrix is, say, B, which is A minus lambda 1 into I. Do you know lambda 1? Yes, it is the dominant eigenvalue of the given matrix A. So, compute a new matrix, call it as B, which is A minus lambda 1 into I, and compute its dominant eigenvalue. So, you are using again power method to compute its dominant eigenvalue. Then once you know its the dominant eigenvalue of A minus lambda 1 into I, then your that eigenvalue plus lambda 1 will give you lambda p, which is the least eigenvalue. So, let us discuss about the corresponding eigenvector. So, if suppose I call x p dashed as the corresponding eigenvector, then A minus lambda 1 into I into x p dashed must be lambda p minus lambda 1 into x p dashed, because lambda p minus lambda 1 are eigenvalues of A minus lambda 1 into I, and the corresponding eigenvector is x p dashed. So, what does this give? This gives you A into x p dashed is equal to lambda p into x p dashed. Why? The next term will be minus lambda 1 I x p dashed, that will cancel with minus lambda 1 x p dashed. So, we get A x p dashed is lambda p x p dashed. What does that give? This gives you that the eigenvector corresponding to the eigenvalue lambda p, which is the smallest eigenvalue of A, is the same as the corresponding eigenvector associated with the eigenvalue lambda p minus lambda 1 of the matrix A minus lambda 1 into I. So, you not only get the smallest eigenvalue in magnitude of the given matrix A, but you also get the corresponding eigenvector. What is it? It is x p dashed. What is this eigenvector? This is the eigenvector which is associated with the eigenvalue lambda p minus lambda 1 of the matrix A minus lambda 1 into I. So, you are able to get the smallest eigenvalue as well as the largest eigenvalue by using power method. So, let us just recall the steps for computing the smallest eigenvalue of a given matrix A. So, you start with the matrix A, get its largest eigenvalue, call that as lambda 1. So, it is the largest eigenvalue in magnitude for the matrix A, call that as lambda 1. Now, form a matrix B which is A minus lambda 1 I. For this matrix you compute the largest eigenvalue. Then the smallest eigenvalue of the given matrix A will be lambda p, such that if lambda p dashed is the dominant eigenvalue of A minus lambda 1 I, then the two are related by lambda p dashed is lambda p minus lambda 1. So, you immediately know what is the smallest eigenvalue of the given matrix. What is the associated eigenvector? You compute the corresponding eigenvector associated with lambda p dashed for the matrix A minus lambda 1 I. That eigenvector is the eigenvector associated with the smallest eigenvalue lambda p of the matrix A. So, that completes our discussion on how we can get the smallest eigenvalue. So, the method does not involve computation of inverse of the matrix A. So, it is much easier to work out, because you again apply power method to a new matrix, and therefore, the computations are very simple. Can we give the locations of the eigenvalues for a given matrix A? The answer is yes. There are results which clearly specify the regions within which, circular disks within which the eigenvalues are located. So, we look into these results, and therefore, we will be able to know where the eigenvalues of a given matrix are located. The following result gives us a way to find the location of eigenvalues of a given matrix A. What does the result say? It says the largest eigenvalue in modulus of a square matrix A cannot exceed the largest sum of the moduli of the elements along any row or any column. Suppose say lambda I is an eigenvalue of an n cross n matrix A. Let us take A has entries denoted by Aij, where I and j run from 1 to n. Suppose xi is the corresponding eigenvector and having components xi1, xi2, etc., xin. Then we know that Axi is lambda I xi. So, if we write out these n equations, then they are of this form: A11 into xi1 plus A12 xi2 plus etc. plus Ain into xin will be equal to, on the right hand side I have lambda I into xi1. Similarly, I take the second row of A and multiply by this column vector and equate that to the second entry in lambda I xi. So, I continue and write down the nth equation. Now, I take modulus of xik to be the maximum of modulus of xij over j. So, once I get that, I take the jth equation and divide the jth equation by xij. So, what will I get? I will get lambda I. So, if I take the second equation and I divide by xi2, then on the right hand side I have just lambda I. So, here I select the jth equation and divide the jth equation by xij. So, that will give you lambda I is equal to aj1, that will be the first term here, aj1 xi1, that divided by xij. Then the next term aj2 xi2 divided by xij, and so on. Then I will have a term ajj xij, I divide it by xij. So, that simply gives me ajj plus etc. plus ajn into xin by xij. So, if I take the absolute value on both sides, then mod lambda I will be less than or equal to mod aj1 plus mod aj2 plus etc. plus mod ajj plus etc. plus mod ajn. Why? Modulus of xik by xij is less than or equal to 1. Why? Xik in absolute value is the maximum of modulus of xij, and therefore modulus of xik by xij in absolute value is less than or equal to 1, and therefore mod lambda I is less than or equal to mod aj1 plus mod aj2 etc. plus mod ajn. What are these? These are the absolute values of the entries that appear in the jth equation, and so j is arbitrary, and therefore mod lambda is less than or equal to maximum over I of sigma over k equal to 1 to n modulus of aik, and that completes the result that the largest eigenvalue in modulus of a square matrix cannot exceed the largest sum of the moduli of the elements along any row or any column. What about the proof for any column? The matrix A and A transpose have the same eigenvalues, and therefore the proof of the theorem holds good also for columns, and hence Gershgorin's theorem is completed. So, we now have another result which gives us the location of the eigenvalues of the given matrix. It is given by Brewers theorem, and it states that if Pj is the sum of the moduli of the elements along the jth row excluding the diagonal element ajj, then it says every eigenvalue of A lies inside or on the boundary of at least one of these circles, which are described as mod lambda minus ajj equal to pj for j is equal to 1, 2, 3 up to n. So, these are circles which have ajj as center and radius as pj. So, there are n such circles, and the result says that every eigenvalue of the given matrix A lies inside or on the boundary of at least one of these circles. That is what Brewers theorem states. The proof is very simple. So, let us work out the details. So, we already have seen in Gershgorin's theorem this step, namely lambda I was written as all these terms plus ajj after dividing by xij. So, I can bring ajj here and write lambda I minus ajj is the sum of the rest of the terms, and therefore, in absolute value mod lambda I minus ajj will be less than or equal to mod aj1 plus mod aj2 plus etc. plus mod ajj minus 1 plus modulus of ajj plus 1 plus etc. plus mod ajn. Why? The reason is modulus of xik by xij is less than or equal to 1 for k running from 1, 2, 3 up to n. And what is this? This is summation I is equal to 1 to n. You see that there is no term mod ajj, so I not equal to j of modulus of aji, but that is what is denoted by pj in the theorem. So, this is equal to pj. So, what are your circles? Your circles are such that they have their centers at ajj for j is equal to 1, 2, 3 up to n, and the radii are given by pj for j is equal to 1, 2, 3 up to n. So, you now know the circles within which the eigenvalues can be located, and the result says every eigenvalue of A lies inside or on the boundary of at least one of these circles which have their center at ajj and radii as pj. So, let us now use Gershgorin's theorem and Brewers theorem to find out the location of eigenvalues of a given matrix A. The circles that we have obtained are called Gershgorin circles, and the bound that we have obtained is called Gershgorin's bound. So, let us try to determine Gershgorin bounds, so that we know where all the eigenvalues of a given matrix are located. So, we have some important observations to make before we proceed with demonstrating these results. So, let us consider these observations. Now, we know that A and A transpose have the same eigenvalues. And therefore, all the eigenvalues lie in the union of the n circles, namely modulus of lambda I minus a j j is less than or equal to sigma k is equal to 1 to n, k not equal to j modulus of a k j for j is equal to 1 2 3 up to n. Then secondly, all these bounds are independent of each other, and therefore, all the eigenvalues of A must lie in the intersection of these bounds. If any of the Gershgorin circles is isolated, then this circle contains exactly one eigenvalue. And if you are given a real symmetric matrix A such that Aij is Aji, then in this case we obtain an interval which contains all the eigenvalues. So, in case you are given a matrix A which is a real symmetric matrix, then you can see that you can obtain an interval which contains all the eigenvalues of this real symmetric matrix. So, let us take an example. Suppose say A is a matrix having entries 3 2 2, 2 5 2, 2 2 3. So, let us now apply Gershgorin's theorem and Brewers theorem and determine the bounds. So, all the eigenvalues of this matrix lie in the interval mod lambda less than or equal to maximum of 7, 9 and 7. What is it? It is the row sum, or it is also the column sum. So, take the first row, take the entries in the first row and compute the absolute value of each of the entries and add it, or take the entries in the first column and compute the absolute value of the entries in the first column and add them, then you get value to be 7. Do that for the second row and the third row, or the second column and the third column. Which theorem have I applied? I have used Gershgorin's theorem. So, I obtain mod lambda to be less than or equal to 9, and therefore, lambda is such that it lies between minus 9 and 9. This is what my Gershgorin's theorem says. What does that mean? I have an interval between minus 9 and 9 in which all the eigenvalues of the given matrix lie. Let us now use Brewers theorem and see what the result is. The Brewers theorem tells us the eigenvalues lie in the union of the intervals given by modulus of lambda minus a11, that is 3, less than or equal to P1. What is P1? The sum of the absolute value of the entries in the first row. So, it is 4. The second condition is modulus of lambda minus a22, which is 5, and that is less than or equal to the sum of the absolute values of the other entries. So, that is again 4. And from the third row we get modulus of lambda minus 3 is less than or equal to 4. Let us look at the first inequality. It gives mod lambda minus 3 less than or equal to 4, mod lambda minus 5 less than or equal to 4. So, minus 4 less than lambda minus 5 is less than 4, 1 less than lambda less than 9, and the third inequality is mod lambda minus 3 less than or equal to 4, which is the same as the first inequality. So, Brewers theorem tells us that all the eigenvalues lie between minus 1 and 7, and lambda, all the eigenvalues lie between 1 and 9. Therefore, we make use of the result obtained using Gershgorin's theorem and using Brewers theorem. The first inequality says the eigenvalues lies between minus 1 and 7. So, it lies in the interval minus 1 to 7. The second inequality says it lies between 1 and 9. So, between 1 and 9, and result from Gershgorin's theorem tells us that lambda lies between minus 9 and 9. So, it lies between say minus 9 and 9. So, now we have to make a conclusion about the interval within which all the eigenvalues lie. So, since the bounds are all independent of each other, so we have to find the intersection of these intervals and write down the interval within which all the eigenvalues lie. So, we observe that the intersection of these intervals is minus 1 less than or equal to lambda less than or equal to 9. So, the eigenvalues of this given matrix lie in the interval minus 1 to 9. So, if the given matrix A is a real symmetric matrix, then you can find an interval within which all the eigenvalues of the given matrix lie. And I will include more problems on Gershgorin's bounds in the assignment sheets.